Hi and welcome to my tutorial about delay alignment using the WaveCapture software. First I will show you two methods. The first is damn wrong and shall not be used. The second shall be avoided in my opinion, as it fools you to align to reflections instead of loudspeakers. This method is found in other measurement systems, tutorials and help files. And the method is damn wrong. It aligns the tops to subs with its energy peaks. And here I'm gonna show you why. We start with a top system representing of a high-pass filter, which I have simulated, and then a sub, also simulated like a bandpass filter. You see the frequency response, and here you see the group delay. We tick the boxes for operate on here for these two measurements and press the align delay, and they will be up here in a separate window. And here we go to change the delay for the top and align it to so it corresponds to the energy peak of each band. And you see the result here that it's not optimum and the group delay curves is far away from each other. Another way to see it is if we can take the total curve here, or the actually impulse response, and copy that to the capture tab. And here we can see the total group delay, but we can also make a wavelet representation of this, and it looks like this. And you can see that it's far from a minimum phase representation. It's more like that the crossover region here is like a linear phase, but the other regions are minimum phase. So it looks like this in 3D. Okay, we go back here and try to make a real minimum phase alignment. We find a crossover point here about 120 Hz, and we enter this number here, and then they can use this delay finder, press that, and it asks if we also should test to make a polarity reverse. We found that the group delay seems to match. We can look here. The group delay match up well here. We can check the wrapped phase. It also match well. And then we can export or copy this impulse response to the capture tab and make the same wavelet analyze here. And here we clearly see that this is a minimum phase alignment, because it says that all frequency will start in time at the same time. Can have also the 3D representation here. I can show you the total group delay and phase response here, and if I move this cursor with the top system, you can see the red trace here, how the group delay will alter. But the frequency response, the blue trace here will be non-flat. But of course, if you trim the top system, you got something like a fake linear phase system at the crossover region, but it still will be two different minimum phase system, because a linear phase system should have constant group delay. Many think that it is a constant phase, but you can never have a constant phase. It's a constant group delay, and you can see that in the wavelet here, that the group delay represents the top of the hill of the ridge of the wavelet. So all energy it's centered at one fixed time. Not useful to make a linear phase system for live PA systems, because it requires an FIR equalization, which must be very long, about 50 to 100 milliseconds, and you can't allow for that processing latency in such system. So the solution is to make a mixed phase system, and I will come back to that in a presentation of FIR capture. Here is the second thought about delay alignment. You should neither use wrapped phase or smoothing. Here we have a top system, raw measurement, and when I start to use windowing, I prefer to, instead of using the impulse response or the energy time curve, I use Kepstrom, because here I can clearly see the reflection from the room. And sometimes somebody like to use smoothing. Of course we can apply that, but I can see a problem, because if we can look at the wrapped phase like this, and we can see the group delay like this. It's a lot of noise, and you can apply the smoothing, of course, here. But the problem is that you will not got the right group delay curve, because it will be some kind of smoothing and averaging here. So if we use a multi-time window instead, you will have the through group delay response like this. And also the wrapped phase, you will see that it's much cleaner, even if it's hard to see the reflection in the wrapped phase, because it will be double wraps when it is a reflection. So I prefer to see the group delay, because every reflection here will represent by a transient in the group delay, and it also indicates that such transient will not be possible to equalize, because it's position dependent. And in such case, it's important to make an average over many measurements. I will come back to that in another presentation. Here is the sub in the same system, and if we look at the group delay, it's very noisy, of course, and we have the same problem here, that if you make a smoothing, you will mess up the phase and group delay measurement. So don't use that, use the multi-time windowing instead. And here you see the response. And one trick to make it more visible is to use the phase blanking. So you cut away the phase information and group delay and so on. When the level have dropped about 30 dB, when the level have dropped so much, the phase have no influence on the response at all, as it even if it's in reverse polarity, it's only makes maybe maximum a quarter of dB to the frequency response. And then we use these two measurement and go to the delay alignment like this. Here we have the sub which need to be delayed to be aligned, and one common thing is to use wrapped phase like this. I will lower the level to increase the visibility a little bit. So here we go, and it's not easy to find. I can turn off the frequency response like this, because we have a lot of reflections in the measurement, and it should be here something like that. But as you see, we have a lot of double wraps in the wrapped phase representation, so it's not so easy to find. And the risk is that if you align with wrapped phase, you will align your system to some reflection instead. So if you instead turn on the group delay, then you can see that even if we have all these transients in the traces, you can make an asymptote to this curve and see that it shall be something like this. We can also test the automatic delay finder here. I have noticed that the crossover shall be around 130 Hz. So if we do like this, you can see that the finder will suggest a delay of 15 milliseconds, but we will also check with a polarity reverse of the sub. But you got this warning here, but that will provide a longer delay time, so we pick the first one instead. Look like this, and then we can check the frequency response. It will look, you see the total curve here will align at the crossover point, and here is the wrapped phase. Of course, we can increase the visibility by moving this phase reference closer to it, so we got less wraps, but it doesn't help so much. You can't determine the alignment delay by using wrapped phase in this case. So what is wrapped phase? If we turn on an unwrapped phase, it looks like this. The problem is that it starts here at about 20 degrees and it stops at with 2000 degrees. So it's very hard to see details. The reason why we have this curve here is that the phase is linear with frequency. So if we change the scale here to linear frequency scale, you see that it's a straight slope. And if we turn on the wrapped face, the idea is that you should see more details, because if you don't wrap the face, I mean already here it's about 2000 degrees, so you need to zoom in this to see details, and maybe if you print it out you need a 10-meter long paper to do that. And that's the idea with wrapped face, but that you zoom in, and this vertical lines here has actually no information, because it's only this curve here which contains the information. Compare that to the group delay. There you can see how the time varies through the system. I will show you an animation to see how the wrapped face is done. Okay, here is the animation. Here you see the unwrapped face, and then we cut it in pieces to form the wrapped face, and that's it. Some lecturers think that is have something to do with the Nyquist helix, and they are bloody wrong, of course. Other thinks it's another helix. I want to show you some further features. First is the phase reference. You will find it when you move the impulse with the least propagation delay, and then you see a yellow cursor which can be moved, and in that way you have a better visibility. You see that on the group delay, and it's even more important for the wrapped face presentation, that you will have less wraps, so you have a better graphical resolution, and you can also dial in the phase reference delay here. The other feature is that you have two cursors here in the frequency domain, so you can zoom in the crossover region like this, and that's also useful wrapped face, so you can see the crossover. Another feature is that these cursors can be used to filter out the impulse response in the crossover region, so you can apply bandpass filters to this area, and in that way you have ability to see how the impulse response looked like. And here is a trick I learned from a good friend called Paul Baumann. He had been director of Hell Acoustic and JBL before, and that is that if you filter out the impulse response, then you can have a very accurate alignment by taking the second oscillation of the top and then align that to the largest swing of the sub, like this. So that is a fine-tuning alignment. You can watch the the wrapped face too, so you can see that it's a little trick to do it. But of course it's very hard to do that if there are a lot of reflections in the measurement. Here are some conclusions. Don't use the energy peak alignment. That will give you a lot of time smearing. Instead, use the minimum phase alignment. Avoid wrapped face, because if you have a lot of reflections in the measurement, then it's hard to find the right alignment. Don't use the smoothing. That will not make the right group delay or phase traces. Use the multi-time windowing instead. And use the group delay for the alignment. WaveCapture software is one of the few measurement software which show the true group delay. There is a delay alignment tutorial on my website, so you can download and see further. It looks like this. And then I thank you for watching, and I look forward for your comments.